Hello Doctor, we would like to present our system model which titled Pharmacokinetic two-compartment model for oral drug administration. Pharmacokinetic modeling is a tool used to help drug developers understand a drug's effect on the body by analyzing its absorption, distribution, metabolism, and excretion properties. It can range in complexity from models with a single compartment to models containing hundreds of compartments. Pharmacokinetic two-compartment model divided the body into central, which include well-perfused organ, and peripheral compartment, which consists of skin, muscle, or tissue, where distribution of drugs is much slower. This study aims to develop two-compartment pharmacokinetic model to better understand the route of drugs that are orally administered into our body.
Moving on to methodology, so based on the anatomical figure designed above, we have designed our own two-compartment model whereby the oral administered drug will move from the gut to the central system through Ka, then it will go to peripheral system through Kc, then it will return back to central through Kp, then lastly go to the excretory system through Ke. So all these processes are represented by the equation on the left side of the page. And in this experiment, we set our own constancies, which can be seen on the right side. And most importantly, the concentration of the drug will remain constant, which is 1.8 milligram. In this system, there will be two flowcharts for the pseudocodes. One will be about system implementation and the other one will be on plotting the results. So first of all, the first flowchart will be on reading the drug concentration, moving from the gut to the central to the peripheral. Only if the system has decided it has passed the peripheral, then it will only go to the excretory system, then the system will end there. The second flowchart will be on plotting the results, whereby it will begin with reading the drug concentration on every stages, which is 4 stages. Then only then it will plot the concentration of the drug in 4 stages. It will plot relative concentration, and lastly it will plot periodic drug uptake for 2 hours and for every 5 hours, and the system will end there.
So here is a discussion on the graph 1. For the G line, we explained that because of its an intakes, we set boundary conditions of 1.8 concentrations, and since it has been absorbed by the digestive tract system, it explained that it falls drastically right after 1.5 hours. And next, for the E line, after 25 hours of observations, we have seen that the concentration has been increased in value for the drug concentrations. Hence, this is wanted that the peak excretion system signifies that the input values and output values are in linear. And lastly, for the C line, central line, and peripheral line, we observe that C line has a little bit lesser in 0.5 concentration than the P line. This is we would like to indicate that the C line focusing on the brain and spinal cord, while the P line focusing on the afferent and efferent neuron system.
Okay. Continue with the discussion. The second graph shows a relative concentration for each stage. The blue line that represents the concentration in GI tract that shows a rapid decrease from 1.8 to 0 in less than 5 hours. So the model showed the elimination of drugs from the gut is within the time range. This is because in real life cases, after the oral administration, the absorption of the drugs into the bloodstream usually takes place around 1 to 6 hours. And as the drug being distributed to the central and peripheral compartment, a shallow slope in concentration represented by the orange and also the yellow line with the presence of time lag can be observed from the graph. So the time lag is due to the impact of the elimination from central to peripheral, and as we can see, the yellow line shows a slower slope due to the distribution of the drugs from central to peripheral in order for them to reach a steady state.
Now we have come to the last part of the discussion. The two graphs basically have the same shape of lines, but the second graph has a bigger scale, thus larger frame of time. The graphs shown that by the end of the 21st hour, the drug had been eliminated from the body. The concentration at the blue line declined from 1.8 mg to 0 within the same period. The process of oral drug absorption used in this study is mainly zero order, and the purple line and blue line up to the 2 hours mark reflect that in both graphs. Then the purple line started exhibiting a first order kinetics of excretion. The concentration of drug in the central compartment decreased to 0 under 10 hours, while for the peripheral compartment went from 0.75 mg to 0 in about 20 hours. However, there is a difference in both graphs, which is the concentration of drug at the excretion phase at the 2 hour mark.